My name is Aulia Rahma Putri, student of Chemical Engineering from Universitas Pembangunan Nasional Veteran Yogyakarta with the study number 135. So I will review the article titled A Comprehensive Review of Chemical Reaction Mechanism and Third Generation Mechanism for Hydrogen and Diesel Addition to Ammonia Fuel and their emission characteristics. This article was published in Science Direct on July 20, 2024. This article was written by Xuan Cui, Xuan Zhou, Qinqing Zhang, Peiyang Liu, and Chuanfu Ko. They are from the institution of Guangxi University of Science and Technology and, and Hunan University in China. The keyword of this article are ammonium wool combustion characteristic, ammonia combustion emission, mixed combustion, and third generation. The abstract of this article, urgency of using renewable energy to support green production and reduce pollutant emission, focusing on ammonia as a potential renewable energy source. The main point of the abstract include ammonia is considered a promising fuel due to its renewable, zero carbon, and environmentally friendly properties. This article explored the use of ammonia in diesel engines, but as a primary fuel and a blend with hydrogen and diesel. This study evaluated the kinetic and combustion mechanism of ammonia in pure form as well as its blend with hydrogen and diesel. The chemical reaction mechanism includes pollutant formation and emission characteristics. The study pays special attention to how fuel blends can affect combustion efficiency and reduce emission of pollutants, such as black carbon and nitrogen oxide. This article highlights the difference in reactant in key reaction and change in reaction mechanism across different combustion conditions. The author examines how the reaction mechanism of the full mixture affect the formation and reduction of pollutants. This article provides deep insight into the potential of ammonia as a renewable fuel, as well as its blends with other fuels to address environmental challenge. It aims to promote further research on clean energy and greener combustion technology. The abstract as a whole emphasizes the relevance of ammonia as a future fuel, but in terms of energy efficiency and reduced environmental impact. The introduction. The introduction section of this article provides important background of the extensive use of fossil fuel since the Industrial Revolution. It highlights the impact increased consumption of fossil fuels such as oil, coal, and natural gas on climate change and air pollution. Key facts include the increasing fossil fuel production and consumption. Data from the internal, International Energy Agency show that coal production increased from 6,000 and 2022 million ton to 7,713 million ton between 2005 and 2015, while global oil consumption increased from 3,900 million ton to 4,000 and 300 million tons over the same period. Environmental impact of greenhouse gas emission. Burning fossil fuels produce carbon dioxide, which account for 56.6% of total man-made greenhouse gas emission. This exacerbates climate change and degrades atmospheric quality. Health consequences of pollutants. Pollutants such as carbon particle and atmospheric aerosol harm human health, causing millions of premature deaths each year. Emission reduction effort. The author mentioned that reducing greenhouse gas emission is a key task in addressing global warming. The transition to renewable energy sources such as hydrogen and ammonia is an important focus to achieve energy balance and carbon neutrality. Advantage of ammonia as alternative fuel. Ammonia is proposed as an environmentally friendly zero carbon fuel with combustion reduction, nitrogen, and water without carbon dioxide emission. However, the use of ammonia faces challenges such as low combustion speed, narrow flammability range, and nitrogen oxide emission. These figures show that the development of the fossil fuel divestment movement from 2011 to 2021, fossil fuel divestment is the process by which institution or organization withdraw their investment from the fossil fuel industry to support sustainability and fight climate change. This graph reflects in the increasing global awareness of the adverse environmental impact of fossil fuels, encouraging institutions to seek cleaner energy alternatives. Large asset of large asset on the move. The significant surge is asset after 2018 show that large institutions with major financial clout are joining the movement, giving a broader impact to global energy transition and support for renewable energy. This divestment not only means a reduction in investment in fossil fuels, but also a possible redirection of those funds to renewable energy sector. This chart highlights the success of the fossil fuel divestment movement over the past decade, with exponential growth in the number of institutions participating and assets diverted. This trend reflects a global shift toward, towards more environmentally responsible investment to support sustainability and climate change mitigation. This figure is schematic representation of the effect of ammonia addition on such formation during carbon-based fuel combustion. The combustion process starts with pyrolysis, the initial stage where the fuel breaks down into smaller molecules due to heating without oxygen. At this stage, stood precursor compounds are formed, such as unsaturated hydrocarbon and aromatic molecules. Furthermore, in the gas phase, polycyclic, polycyclic aromatic hydrocarbons compounds are formed from the pressure, pressure. Polycyclic aromatic hydrocarbons are ring-shaped aromatic compounds that are precursors of soot particles. The addition of ammonia can affect the formation of soot precursor in the gas phase, reduction or changing the pathway of polycyclic aromatic hydrocarbon formation. In the solid phase, polycyclic aromatic hydrocarbon combine to form small core particle known as shoot nucleation. The addition of ammonia can affect the morphology at this stage, such as reducing the particle size and it changing its aggregate structure. Subsequently, the subcore particle undergo growth through aggregation or addition of molecules from the gas phase. Ammonia affect the quantity of soot products and the physical structure of soot at this stage. In the final stage, soot oxidation, soot particle can be oxidized into simpler gas such as carbon dioxide. So ammonia can affect the nanometric structure and reactivity of soot, which can increase the soot oxidation rate and reduce solid particle emission. Overall, in the addition of ammonia affects several aspects in soot formation, including the reduction of soot precursor, change in soot morphology, reduction in the amount of soot products, as well as changing in the nanostructure of soot, which make it easier to oxidize. This figure shows that ammonia can help reduce soot emission by affecting the formation pathway and physical properties of soot at different stages of the combustion process. The economic analysis of hydrogen and ammonia in diesel engines. Section of the journal discussed the economic aspect related to using hydrogen and ammonia as alternative fuel in diesel engines. While hydrogen and ammonia offer the potential to reduce greenhouse gas emission and pollution, their application in diesel engines requires careful cost analysis. Hydrogen production costs are still relatively high, especially for a green hydrogen produced through water electrolysis using renewable energy. Likewise, while ammonia is a cheaper and easier to store than hydrogen, its production process, which relies on green hydrogen, still requires significant investment. Despite the high initial costs, research show that the use of hydrogen and ammonia in diesel engines can reduce fossil fuels consumption and improve the engine thermal efficiency, contributing to long-term operational cost savings. In addition, the use of hydrogen or ammonia blends can reduce emission costs through carbon dioxide reduction, providing economic benefit through environmental incentive and carbon penalty reduction. In terms of influence in, in terms of influence on engine efficiency, hydrogen and ammonia blends can also reduce nitro, nitro oxide and particulate emission, which can further reduce emission treatment costs and extend engine life. Overall, despite challenges in initial cost and infrastructure, the potential for long-term cost saving and environmental incentive make hydrogen and ammonia an attractive attractive alternative fuel for diesel engine in the future. The chemical reaction mechanism of ammonia. Section of the journal discuss the chemical reaction mechanism that occurs during ammonia combustion and how ammonia interact with oxygen and other radicals in the progress and in the process. Ammonia combustion ammonia combustion involves interact with oxygen. Ammonia combustion involves a series of complex reactions which begin the composition of ammonia into ammonia combustion involves a series of complex reactions which begin with the composition of ammonia into NH2 and hard radical at high temperature. This reaction initiates an oxidation pathway that then produces nitrogen monoxide as the main byproduct. In addition, ammonia can produce nitrogen dioxide and other oxidizing compounds, which are highly dependent on combustion temperature and oxygen availability. Nitrogen oxide formation occurs more through the full nitrogen oxide pathway, which is directly related to the nitrogen in the fuel itself, than the thermal pathway, which is more dominant at high temperature. The mechanism also involves the formation of other radicals, such as hydroxide and hydrogen. which play an important role in the further combustion reaction and in the control of nitrogen monoxide formation. One of the main challenges of ammonia combustion is the formation of nitrogen oxide, which although can be reduced by control of combustion temperature and condition, remains a major pollutant in an incomplete combustion condition remains a major pollutant. In addition, unburned ammonia can also be released into the atmosphere, especially under incomplete combustion condition. Therefore, the chemical mechanism of ammonia combustion is greatly influenced by temperature, air, air, air full ratio, and the presence of other radicals, all of which contribute to combustion efficiency and resulting emission. The section on combustion characteristic and pollutant generation of ammonia. In the journal discuss the combustion properties of ammonia as a whole, focusing on its environmental impact, particularly the formation of pollutants. Ammonia is a carbon-free fuel. Ammonia is a carbon-free fuel, meaning it doesn't produce carbon dioxide when burned. Ideally, the complete combustion of ammonia produces only nitrogen and water vapor, which is environmentally friendly. However, ammonia has some limitation in combustion, such as a high ignition temperature, a narrow flammability range, and low flame speed, making it less stable compared to conventional fossil fuel like diesel or hydrogen. A significant challenge in ammonia. A significant challenge in ammonia combustion is the formation of nitrogen oxide, which is primarily caused by the nitrogen present in the fuel. Ammonia combustion produces nitrogen oxide mainly through the fuel combustion pathway, especially at lower temperature with thermal nitrogen oxide playing a less role. Additionally, ammonia combustion can lead to the production of nitrous oxide, a potent greenhouse gas with much higher global warming potential than carbon dioxide. The formation of nitrous oxide is strongly influenced by combustion temperature, with the fuel pathway being the major contributor. The ammonia energy ratio is a key factor in controlling both emission and combustion efficiency. Research indicates that as the ammonia reserve ratio increase, there is a rise in nitrogen oxide and nitrous oxide emission, particularly at lower combustion temperature. At higher ammonia energy ratio from 40% until 60%, nitrogen oxide emission increase even though carbon dioxide and particulate matter emission decrease, suggesting the ammonia combustion while producing carbon dioxide can also contribute to increase nitrogen oxide emission to increase nitrogen oxide emission. To mitigate this emission, technology like selective catalytic reduction or SGR and exhaust gas recirculation atau EGR can be employed. Selective catalytic reduction helps reduce nitrogen oxide by converting it into nitrogen and water at a temperature between 300 until 420 degrees Celsius, while exhaust gas recirculation lower the combustion temperature by recirculating some exhaust gas back into the combustion chamber, thereby reducing nitrogen oxide, nitrogen oxide formation. In conclusion, while ammonia holds promise as a clean fuel that reduces carbon dioxide emission, managing the formation of nitrogen oxide and nitrous oxide remains a significant challenge. Post-combustion technology like selective catalytic reduction and exhaust gas circulation can help mitigate this pollutant, but further research is need to optimize ammonia combustion, particularly for internal combustion engines and large-scale application. Based on the figure, is the beach, a carbon-free ammonia-based circular economy system based on the Journal of McFarlane et al. 2020. Renewable energy sources such as wind turbines, solar panel, and water power are used as the main power source to generate electricity that is used to power electrochemical conversion process. Through this process, nitrogen taken from air and water is split into hydrogen using electrolysis. This reaction produces ammonia as the final product, while becomes a carbon-free energy carrier. The ammonia produced is stored in storage tanks and then distributed through pipelines, land transportation, and shipped for local and global needs. The ammonia produced is used in various sectors, namely in the transportation sector as a fuel for ship and aircraft, while in the industrial sector as a raw material for fertilizer and pharmaceutical products. In this cycle, the nitrogen produced through ammonia combustion will return to the atmosphere and become part of the natural nitrogen cycle. This ensures that the use of ammonia produces no carbon, making it natural nitrogen cycle. This ensures that the use of ammonia produces no carbon, making it an environmentally friendly fuel. This process creates a circular economy as the fuel ammonia is produced, used, and recycled through the nitrogen cycle. And energy required for ammonia production comes from from renewable source, resulting in no additional carbon emission. The combustion characterization and pollutants generation of ammonia hydrogen. The section of this journal discuss the combustion characteristic and pollutant generation resulting from the combustion of mixture of ammonia and hydrogen. Combustion of this mixture increase reactivity and flame speed because hydrogen, as a highly real as a highly reactive fuel, help accelerate the combustion process by increasing the formation of oxygen and hydrogen radicals. These radicals accelerate accelerated accelerate the combustion process, resulting in more efficiency combustion. However, this increased reactivity also affects the flame temperature and composition of the combustion product, potential affecting the formation of pollutants. Although ammonia is a carbon-free fuel, combustion of ammonia and hydrogen mixture still result in nitrogen oxide emission, mainly due to the reaction of nitrogen from ammonia with oxygen at high temperature. This process, known as full nitrogen oxide formation, is more predominant in lean combustion where more oxygen is available. However, under rich combustion condition, the denitrification process is dominant, which reduces nitrous oxide emission but increase the formation of nitrous oxide, a more harmful greenhouse gas. The addition of hydrogen in the mixture increase the flame temperature, which exacerbates nitrogen oxide formation at in condition, but also have reduced carbon dioxide and particulate emission, as the hydrogen burns cleanly without producing carbon. Overall, combustion of ammonia and in hydrogen blends offer the potential for cleaner combustion, but also process challenge in the management of nitrogen oxide and nitrogen dioxide emission. Controlling combustion condition, oh, sorry, in the management of nitrogen oxide and N2O emission, N2O emission. Controlling combustion condition for mixture full mixture, mixture, full mixture ratio, and applying emission control technologies such as activity catalytic reduction and exhaust gas recirculation are required to reduce the environmental impact of the resulting pollutants. These figures show how an industrial emission control system based on selective catalytic reduction can reduce key pollutants such as such as nitrogen oxide and SO2, but has the potential secondary impact of forming fine particle due to the reaction between ammonia and asam sulfate. The implementation of advanced technologies such as wet flow wet flue gas desulfurization help minimize this emission before they are released into the atmosphere. The Commission of Characterization and Pollutant Generation of Ammonia Dissolved section of this journal discuss the combustion of mixture of ammonia and diesel in dual fuel mode and its impact on combustion characteristic and pollutant generation in dual fuel mode. In dual fuel mode, the addition of ammonia helps improve combustion by reducing the amount of carbon burned and improving the combustion rate, which contributes to the reduction of carbon dioxide emission. In addition, combustion temperature tend to lower compared to single diesel combustion. In addition, combustion temperature tend to be lower compared to single diesel combustion, which contributes to lower nitrogen oxide and carbon monoxide emission. However, However, increasing the ammonia energy ratio can increase nitrous oxide formation, especially ammonia energy ratio above 60%. At an ammonia energy ratio of around 35%, the combustion showed the best result with a 23% reduction in carbon monoxide and 20% reduction in nitrous oxide emission compared to single diesel combustion. In addition, this dual mode proved to be stable even when operated at higher altitudes where the intake mass flow and excess air coefficients decrease. This show that ammonia diesel combustion is not only effective at sea level but also at lower pressure atmospheric condition. Overall, although the dual fuel ammonia diesel combustion successfully reduced the carbon dioxide and nitro oxide emission, ammonia 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 energy ratio, control and optimization of combustion condition are required to minimize N2O formation and achieve an optimal balance in emission reduction. Emission characteristic of ammonia combustion. Section of the journal discuss the emission resulting from ammonia combustion, including nitrogen oxide, unburned ammonia, and nitrous oxide. and a factor that influence their formation. Nitrogen oxide is the main pollutant produced with its formation influenced by combustion condition, both lean and rich. Under lean condition, high oxygen availability is accelerated nitrogen monoxide formation through hydroxyl radical reaction that convert ammonia to HNO, an important intermediate compound in the nitrogen monoxide production pathway. In contrast, under rich condition, hydrogen-rich radicals such as hydrogen promote the formation of nitrogen oxide radicals, which produce N2H compound N2H compound supporting the oxidation of ammonia without excessively increasing nitrogen oxide formation. For emission mitigation, a full air equivalence ratio control in the range of 1.5 until 1.2. The range of 1.05 and until 1.2. Proof effective in reducing nitrogen oxide emission by optimizing ammonia oxidation before it produces nitrogen monoxide. In addition to nitrogen oxide, unburned ammonia emissions are also challenged, especially under oxygen-rich conditions where some ammonia is incompletely oxidized. However, at the optimal equivalence ratio, the release of unburned ammonia can be minimized. Emission of nitrous oxide, a potent greenhouse gas, can also from during ammonia combustion, especially in the wet condition due to the more dominant nitrogen oxide radical. In ammonia combustion with hydrogen addition, nitrous oxide emission can be suppressed under rich condition, although nitrogen oxide emission increase under lean condition due to increased reactivity of oxygen in hydrogen radicals. The ammonia diesel dual fuel The ammonia diesel dual fuel would provide an alternative to reduce emission, especially carbon monoxide and nitrogen monoxide through carbon dioxide and monoxide through thermal denitrification reaction. However, nitrous oxide emission tend to increase at ammonia energy ratio above 60% at an ammonia energy ratio of around 35%. Carbon monoxide emission can be reduced by 23% and Nitrogen oxide reduced by 20% compared to single diesel combustion. For optimal result, allow the moderate amount of pilot fuel injection are recommended. Overall, ammonia combustion result in complex emission, but through controlling the equivalence ratio using dual fuel and optimizing combustion condition and the environmental impact can be minimized. Nitrogen oxide remains a major challenge, but approaches such as oxygen enrichment and optimized fuel SEL offer promising solution. The next, the emission characteristic of ammonia, hydrogen combustion. Hydrogen combustion section of the journal discussed the emission pattern resulting from the combustion of ammonia and hydrogen mixture and their effect on key pollutants such as nitrogen oxide, unburned ammonia, and nitrous oxide. In ammonia, in ammonia, hydrogen and air mixture, the addition of hydrogen increase oxygen and hydrogen radicals, which accelerated combustion reactivity and increase flame speed. This result in more efficient combustion, but also increase nitrogen oxide emission, especially under lean combustion condition, in contrast under rich condition. Also, this result is more efficient combustion, but also increase nitrogen oxide emission, especially under lean combustion condition. In contrast, under rich condition, nitrogen oxide emission are lower because the nitrification process dominate, while nitrous oxide emission increase. Hydrogen in the mixture increase the maximum flame temperature and heat release rate, which affect the emission characteristic. When the ammonia hydrogen ratio is very and emission patterns show that hydrogen addition significantly increase nitrogen oxide formation under lean condition, while under rich condition, nitrous oxide emission become more dominant. Meanwhile, rich full ratio provide advantage in reducing nitrogen oxide and nitrous oxide emission, but requires strict control on the proportion of hydrogen to maintain combustion stability. The study also noted that in full rich combustion, net in natrium ini kok natrium nitrogen radicals such as NH and NH2 play an important role in reducing nitrogen oxide formation, while in lean combustion, oxygen and hydrogen radicals from hydrogen accelerated the chemical pathway that produce nitrogen oxide. Therefore, the characterization of emission from ammonia hydrogen then show that although hydrogen can improve combustion efficiency, control of combustion condition, and fuel proportion in essential to minimize environmental impact, especially in terms of nitrogen oxide and nitrous oxide emission. This figure highlights how variables such as break mean effective pressure or BMEP and full mixture composition affect nitrogen monoxide emission in nitrogen oxide. Emission in pure ammonia and ammonia hydrogen mixture combustion. In pure ammonia combustion, an increase in BMEP tend to increase nitrogen oxide emission, but in ammonia hydrogen blends, the addition of hydrogen tends to significantly decrease nitrogen oxide emission, especially at lower engine speed. The emission characteristic of ammonia diesel combustion section of the journal discuss the emission pattern produced when ammonia is used as full additive in dual fuel mode with diesel. The addition of ammonia in diesel combustion can reduce carbon dioxide and nitrogen oxide emission thanks to the thermal denitrification process that occurs. This is due to the reaction between ammonia and oxygen, which reduce the formation of nitrogen monoxide via the reduction pathway, especially at higher temperature. In addition, this dual fuel combustion reduces In addition, this dual fuel combustion reduces the combustion temperature, which contribute to the reduction of carbon monoxide and nitrogen oxide emission. However, despite the reduction in carbon dioxide and nitrogen oxide emission, nitrous oxide emission can increase as the ammonia energy ratio increase. At ammonia energy ratio above 60%, nitrous oxide emission tend to be higher due to incomplete ammonia oxidation process. To achieve an optimal balance, an ammonia energy ratio of around 35% show the best result with carbon monoxide emission reduced by 23% and nitrogen oxide reduced by around 20% compared to single diesel combustion. This dual fuel mode also proved to have stable performance at higher altitudes, even though the intake mass flow and in excess air coefficient decrease. Overall, ammonia diesel combustion provide advantage in terms of carbon dioxide and nitrogen monoxide emission reduction, although special attention should be paid to the increase in nitrous oxide emission under certain conditions. From this figure, pollutant emission in IDD, IDADDF, ammonia diesel dual fuel engines are strongly influenced by the air fuel ratio. As the air full ratio value increase, carbon monoxide emission generally decrease, while nitrogen oxide emission tend to increase. Ammonia emission show a more complex pattern and can vary depending on the operating condition. The conclusion section of the journal discussed the potential challenge, the solution related to the use of ammonia as a clean and sustainable alternative fuel. Ammonia is considered a carbon-free fuel with a high carbon content, 17.8% by mass, making it effective as an energy carrier. Compared to liquid hydrogen, ammonia has a higher volumetric energy density and lower storage and transportation costs. However, its use faces challenge, including low laminar combustion rates, 6 until 8 centimeter per second, high initiation, high ignition energy requirements, and significant nitrogen oxide emission, especially under lean or rich combustion conditions. Several solutions are proposed to optimize ammonia combustion. Combustion under oxygen-rich condition can increase the combustion rate to near methane air combustion, although this may result in unburned ammonia emission. Controlling the full air equivalence ratio at around 1.1 prove effective for reducing nitrogen oxide emission while limiting unburned ammonia. A slightly rich ratio with 1.05 until 1.2 significantly reduce nat- nitrogen monoxide emission by breaking down unburned ammonia. In addition, the addition of hydrogen increase oxygen, oxygen and hydrogen radicals, which accelerated combustion but can increase nitrogen oxide emission, especially under lean condition. However, under rich condition, hydrogen addition result in lower nitrogen oxide and nitrous oxide emission than lean combustion, as well as higher maximum flame temperature and greater heat release rate. The dual fuel ammonia or diesel mode offers an attractive solution to the challenge of ammonia ignition in engines. This mode not only significantly reduces carbon dioxide emission, but also lower nitrogen monoxide emission through thermal denitrification reaction. The use of an optimal ammonia energy ratio also has a significant impact on emission. At an ammonia energy ratio below 60%, the flame temperature is reduced, resulting in lower nitrogen oxide emission, while at an ammonia energy ratio of 35%, there is a 23% reduction in carbon monoxide and 20% reduction in nitrogen oxide emission compared to single diesel injection. At higher altitudes, although the intake mass flow and excess air coefficient decrease, the thermal efficiency remains stable, thus ensuring good combustion performance. In conclusion, ammonia show a great potential as a sustainable fuel with the right optimization strategy to overcome the associated technical and environmental challenge. That's all for me. Thank you.